Imagine heating gold to a temperature hot enough to put the sun's surface to shame. Yet somehow, it refuses to melt. This mind-bending result flips a century of scientific assumptions on their head, leaving experts scratching theirs. But here's where you'll want to pay attention. Researchers have managed to heat solid gold to a staggering 19,000 kelvins. That's a scorching 33,740 degrees Fahrenheit, which is over 14 times higher than gold's known melting point. Incredibly, the gold stayed solid, breaking all the rules taught in physics for generations. How is this possible? For decades, the prevailing belief, built on the so-called entropy catastrophe theory, has held that no solid could survive at more than about 3 times its melting temperature. This theory is based on the idea that as you heat a solid, its atoms shake with increasing ferocity. Eventually, that shaking should beat the material into disorder, causing it to collapse into a liquid. But the latest study, published in Nature on July 23, 2025, throws a wrench into this accepted wisdom. What makes these findings even more astounding is the high-tech method the scientists used. A team from SLAC National Accelerator Laboratory, the University of Nevada, Reno, and a host of international colleagues developed a breakthrough technique for measuring the temperatures of materials under such extreme conditions. Traditional thermometers would vaporize in an instant at these temperatures, so the researchers used ultra-fast X-ray laser pulses. Think of them as lightning bolts that last just 45 femtoseconds, that's 45 quadrillionths of a second. By observing how the atoms inside a super-thin gold foil vibrated under these intense bursts, the researchers could directly gauge the temperature and see how the gold behaves. Here's the truly controversial twist. Even at 19,000 kelvins, the gold didn't melt or become chaotic. Instead, it stayed orderly and crystalline. The reason? The heating happened so rapidly that the atoms didn't have time to fly apart and destroy the solid structure. This raises a provocative question. Have we underestimated how much heat a solid can really handle? Or does gold have extraordinary properties we've only just begun to uncover? Could other materials survive at such extreme temperatures if blasted with heat quickly enough? The implications stretch far beyond laboratory curiosities. For material scientists, this could revolutionize how we design substances to survive in the most punishing environments, such as inside the reactors of future fusion power plants, or deep in the hearts of planets and stars where temperature and pressure soar. This research even arms astrophysicists with better ways to replicate and understand the so-called warm, dense matter state found in extreme cosmic environments. But here's the part most people miss. The new method of temperature measurement is a game changer. By giving us a way to reliably assess the behavior of matter under such intense conditions, scientists now have a tool for sharper, more accurate models of things like planetary formation and energy production systems on Earth. Yet not everyone will agree with these results. Are the long-held laws of physics really up for rewriting, or is this phenomenon limited to special cases with gold and rapid heating? What do you think? Has science just witnessed a bizarre outlier, or are we on the cusp of discovering new rules for the building blocks of matter? Let's hear your take. Do you agree with the researchers, or does this challenge your trust in physics? The debate is just heating up.